It's not always easy, but you can use numbers to describe the height of something, or someone, above the surface of the Earth. When the value gets to 0, that something is on the ground. And conversely, when the value is above 0, it's up in the air, usually being pulled down by gravity. A landing might be gentle, or it could get rough. But for most things up in the air, it's just a matter of time until their height equals 0. We can describe motion using functions, often polynomial functions, like this one. They express relationships, such as between locations in different dimensions, between location and time, or between speed and time. Knowing when a function's value is 0 is often useful for knowing what's going on with an object in motion. You can analyze functions to figure out things like this. For example, analyzing a function that expresses height as a function of time can allow you to project when an object will hit the ground. A root of a function is a value of the independent variable that makes the function's value 0. Let's explore some methods of finding roots of polynomial functions. In baseball, a hit's a hit, no matter how it's achieved. Whether it's a hard-hit line drive or a softly hit blooper, its distance to the ground reaches 0 before a player can catch it. How long does that take? It depends on how high it's hit, and that depends on the upward velocity of the ball when it comes off the bat. Suppose the outfielders are playing about 50 yards apart. Say a batter hits a ball into the outfield about halfway between the outfielders. And suppose it's hit from a height of 3 feet above the plate with an initial upward velocity of 50 feet per second. That's about 34 miles per hour upward. That means that this function describes the distance between the ball and the ground at any time, t seconds after it's hit. The first term's coefficient, -16, is half the acceleration of gravity on Earth in feet per second squared. The second term's coefficient is the ball's initial velocity upward in feet per second. And the third term, the constant, is the height of the ball off the ground in feet when it was hit. We can use this function to calculate how long it takes for the distance between the ball and the ground to get to 0. That's when the ball hits the ground, and it's the same as asking what a root of the function is. Let's test whether the ball is still up at 3 seconds. This is about the time for 2 fast outfielders to get to the same spot halfway between them, if they start about 50 yards apart. At t equals 0, the ball leaves the bat at a height of 3 feet. Evaluate the function for t equals 3. At 3 seconds, the ball is still 9 feet above the ground, so a fast outfielder might get to it before it lands. Let's see if it's down yet at 3.5 seconds. Here's its height then. The value of the function is negative, which means that if the ball could keep going, it would be at a negative height. That is, it would be underground. Impossible. So clearly, it's landed by 3.5 seconds. The root of the equation, the time at which the value is 0, must be between 3 and 3.5 seconds. You know that because the value for height is positive at 3 and negative at 3.5. Try 3.2 and the value is nearly 0. It's just slightly negative, about -0.8. So the root is just a little less than 3.2. If you were to try 3.18, you would find this value, 0.2. You can see this value on a graph of the height of the ball versus time, where the graphed curve hits the height of 0 before it goes negative. You know the value is close to 3.2 seconds for the ball to reach the ground. So depending on the speed and positions of the outfielders, hitting the ball upward at 50 feet per second may give the ball the right height to achieve a single, beyond the infielders, but without it being caught by the outfielders. When a 15-foot wave crashes onto a beach, it releases energy that could be harnessed to generate electricity. That's why these Scottish scientists are studying the energy that ocean waves carry. One of their laboratories is a rectangular wave tank. The more fluid in the container, the more pressure there is on the fluid at the bottom, and the faster it will flow out. That's because gravity pulls the fluid down. That is, as the tank empties, the amount and therefore the weight of fluid goes down. The pressure of the fluid at the hole in the bottom decreases, so the rate the liquid flows out changes over time. Let's suppose the scientists need to drain this huge tank, and they want to know how long it will take. Suppose the engineers have provided this function for volume remaining in gallons. The amount of fluid left is a function of time in minutes after the draining starts, including the square of the time, expressed in a quadratic polynomial. V is volume and T is time. You can see that at time 0, the first two terms drop out as zeros, giving the full capacity of 40,000 gallons, the starting amount. To get the emptying time, we're looking for the value of T at which the volume in the tank, V, reaches 0, a root of the function. A root is a value of the variable that makes the value of a function 0. Since this is a quadratic equation, one way to figure out a root, or roots, is to use the general quadratic formula, which provides roots of quadratic equations. It's derived by solving the general quadratic equation for x when the value of the quadratic expression is 0. This is the quadratic formula. From the engineers, these are the values for a, b, and c in the expression for the volume of water in the emptying tank. C is 40,000, the number of gallons of water in the tank. Substitute these values into the quadratic formula and you get the root, or roots. So T equals about 120 plus or minus 0. And the time for emptying the tank is about 120 minutes, or 2 hours. The discriminant, the part under the square root sign, is 0. When the discriminant equals 0, the equation has only a single root. This is reflected in a graph that touches the x-axis at one point, as does the one for this equation. Here, the root is 120, meaning the tank empties in 120 minutes or 2 hours. If the discriminant were positive, there would be two roots, one adding and one subtracting the radical part of the formula. And if the discriminant were negative, there would be no real roots. These surges of water may someday turn out to be a great source of renewable, cheap, and clean energy. Ah, fall is in the air. Temperatures plummet, leaves cascade to the ground. And pumpkins fly through the air. Yes, November means it's pumpkin chunkin' time in Millsboro, Delaware, when post-Halloween pumpkins are turned into projectiles. It's all part of an annual contest to see whose contraption can launch a pumpkin projectile the farthest. On a graph, the path after release might look something like this. Assuming air resistance doesn't come into play, the projectile's height over time is a quadratic polynomial function of time. It's quadratic because the highest power of the input variable for the function, here time, is squared. The quadratic expression has three terms. The second order, or quadratic term, has a coefficient related to the acceleration of gravity, half of it. The first order term has a coefficient equal to the initial upward velocity of the object, 76 feet per second, or about 52 miles per hour. And the constant reflects the initial height of the object, 20 feet. How long will the pumpkin stay up in the air? To find out, find a root of the function, a value of t for which the value of the function is 0. That's when the pumpkin hits the ground, with a height of 0. Set the function equal to 0, and this is the equation. In some cases, a polynomial can be manipulated to factor it into the product of lower-order polynomials. A quadratic polynomial can typically be factored into the product of two first-order polynomials. Finding the factors can sometimes be a challenge, but when it's feasible, the roots of the function the polynomial expresses can be easily determined from the factors. So let's try factoring the pumpkin's height polynomial to solve the problem. To make it easier to factor, multiply both sides by -1 and divide by the common factor for the coefficients, 4. This doesn't change the right side. 0 times -1 and divided by 4 is still 0. But it makes the expression easier to handle for factoring. The next step is to prepare the form of the factors, with a place for two single-degree expressions. With a little trial and error, you can determine that if you have 4t in one and 1t in the other, and for constant terms, a 1 and a -5, the product will be the reduced quadratic polynomial. So the reduced quadratic expression can be factored into these two expressions. And the roots of the function defined by this expression would be the values of t that would make it equal to 0. Of course, the only way for this to equal 0 is if one of the factors is 0. So either t minus 5 equals 0 or 4t plus 1 equals 0. This works if t equals 5 or t equals minus 1/4. The answer is that the pumpkin stays up either 5 seconds before hitting the ground when h equals 0, or it stays up negative 1/4 of a second. The only answer that makes sense given the actual launch is 5 seconds. But, as the graph of height versus time implies, the same trajectory could have occurred if the pumpkin had been launched from ground level. That is, from h equals 0, starting at t equals negative 1/4, 1/4 second before the actual launch happened. We can check our answer by inserting it back into the original polynomial expression. And yes, a time of 5 seconds does result in a value of 0 for the height. There's more than one way to fling a pumpkin, some easier than others. As for polynomials, it's often useful to see if a quadratic or higher order polynomial has an easy way to be factored. That way, it's easy to find a root, or simply to simplify it.